right? So under the reduction of metal oxide, we are going to learn the third method, because the first and the second we have already learned. What was the first method? It was chemical reduction. Chemical reduction method. And under chemical reduction, there were reduction with carbon and reduction with carbon monoxide. Next one we looked at was a reduction by other metals. Third one was self-reduction method. Under self-reduction method, so this is also called as auto-reduction or also air reduction. So, to which ores do we use this in specific? If at all we have sulfide ore of some of less electropositive metals like sulfide ore of less electropositive metals like mercury, copper, lead, antimony, etc. As it's called as air reduction, they are heated in air. So the part of this ore or part of this compound is changed into either their oxides or sulfates. Then this react with the remaining part of sulfide ore. The remaining part of sulfide ore. To give its metal and sulfur dioxide gas. So example, let me write. If you have mercury sulfide reacting with oxygen, we are having HgO plus SO2. Now this some part of HgO whichever is reacted, this is going to react with the other half of the ore which is left, and where you're getting Hg plus SO2 again. So these are two reactions that are happening. Similarly with any other thing also, if it is lead oxide, lead sulfide, no? Because it's only sulfide ores we're talking about. Lead sulfide ore reacts with oxygen to produce lead sulfate, and half of it is only converted, no? Again it's going to react and it's going to form lead plus sulfur. So two reactions are happening here. Two reactions are happening. There are also the other reaction where the same lead, if it's reacting with oxygen, the possibility of forming lead oxide is also there. Again, the same, some part of lead oxide is going to react with the sulfide ore, and we have the metal and the sulfur dioxide. This is about the self-reduction, and we are done with the third type of third method. We have to look at the fourth one, which will be the last one. Let me know if I can clear, ma. Adyasha, Anjali, Gaira, and Mohammed, if you can just drop a message, yes. We'll clear the screen and go for it.
Ma'am, you can clear it.
Can I clear? What was it, ma?
Yes.
Okay. The fourth one is electrolytic reduction. Electrolytic reduction. This is the most powerful method of reduction. Okay, it's actually powerful method, and also it gives pure product, more purity. But electrolytic reduction is actually, compared to other chemical methods, more expensive. But we use this for very reactive metals such as magnesium or aluminium, or generally for producing high purity samples. And mainly this is used for copper, because it, in this way we actually recover valuable contaminants like silver also in this method. So what is the medium? That is, in aqueous solutions, it is actually more convenient and cheap because it's water, no, aqueous. And products do not react with water here, then you can use it. So what all metals, copper and zinc are obtained with this method of electrolysis of their sulfates. In other solvents, what is going to happen? Instead of aqueous solution, we have other solvent other than water. We can fluorine reacts violently with water. That is why it is produced by electrolysis of KHF2 dissolved in HF. Next, infused metals. Infused metals. So elements which that generally react with water, they are extracted from fused metals of ionic salts. So elements that react with water are extracted from fused metals of their ionic salts. Actually, aluminium is an example. Aluminium is an example which is extracted by fused mixture of Al2O3 and cryolite. But we will learn this in detail with the aluminium extraction. So this is this much only about the electrolytic reduction. Let me know if you're done copying. We'll go to the next one. So I'm clearing it. Next we have okay. So we have thermodynamic principles of metallurgy and applications. Under which we'll talk about electrochemical principles of metallurgy. Electrochemical principles of metallurgy. So when we have electrolytic reduction that has occurred, okay, so we can consider this as a technique for driving the reduction. Like we are helping the reduction to happen it through electrodes and external circuit, because we need electrodes and also you need external energy, electricity, to a reactive or a physical process with more delta G, more negative delta G. See, what are we doing here is the free energy available from the external source can be assessed from the potential it produces across electrodes using this relation. Delta G is equals to minus NFE. So what is each one standing for? N is number of electrons transferred. F is Faraday constant. F is 96.5 kilojoule per mole. E naught also we can call it as, which is electrode potential. So for example, the total gives free energy of the coupled, means internal and external process, is delta G internal plus delta G external is equals to delta G minus NFE external. If potential difference of the external source exceeds then E external is minus delta G by NF. So we have an important point after this. So I'll clear the first. So remember that more reactive metals, very important point. More reactive metals have large negative values of electrode potential. So their reduction is difficult. So if you have two metals, okay, if difference of two in negative values correspond to positive E naught, means difference is in positive, and obviously consequently negative delta G naught. In the equation, delta G is equal to minus NFE. Then less reactive metal comes out of the solution. And more reactive metal goes to the solution. So for example, Cu2 plus Fe solid aqueous gives rise to Cu solid plus Fe plus 2 aqueous. Next, we have a small concept called hydrometallurgy. If I can clear this, we'll start with hydrometallurgy. So I'm clearing the screen. We have hydrometallurgy. Hydrometallurgy means the processing of ores and minerals as well as metals and their compounds at relatively low often ambient temperatures, employing aqueous solution. This is only known as hydrometallurgy. For what do we use this? We use this method generally to used for low grade ores. Copper is extracted by this method. So copper is extracted by hydrometallurgy from a low grade ore, obviously. And it is leached out. Leaching is a chemical method, that's it. And it is leached out using acid reacting with the chemical and bacteria. So what are the methods, steps involved? First is dissolution of the valuable metal in aqueous solution. Next, leaching. Next, purification of leach solution and recover of metal from the purified solutions by electrolysis or by adding electropositive method. These are the 3 steps. Let's look at some examples under this. I'm clearing it. Let us look at some extraction of metals which are obtained by hydrometallurgy. I'm clearing it. First, extraction of silver and gold. So how can this extracted? These can be extracted by precipitation by of their salt solutions by electropositive metals like for example zinc. So what happens first is the metallic silver is dissolved from its ore in NaCN solution. Solute obtained is treated with zinc. When Ag is precipitated. Okay. Now, air is blown into the solution and oxidize Na2S. Also, leaching the metals means reacting. Leaching is chemical method. Leaching with Cn minus ion, leaching the metals like silver and gold with Cn minus ion, the reaction is an oxidation reaction. So what happens here? First of all, it's Ag2S. We try to react with Cn minus. We have 2 Ag Cn2 minus. Cn2 minus plus S minus S2 minus. Okay. Next, the same 2 AgCN twice minus will be reacted with zinc solid, and I have ZnCN4 2 minus plus Ag. This is how we get the silver. Similarly, here you can see Zn acts as reducing agent, and the same reaction would be there for gold also. Okay, if you want me to write for gold also, I'm just writing because they might ask you anything. So if I have to write the balanced reaction, it is 4 Au Cn2 minus plus 4OH minus, and the same 2 AuCN2 minus reacts with zinc, gives rise to ZnCN4 2 minus plus 2 Au solid. This is silver solid. So this is how we extract gold and silver. Next, we have the extraction of aluminium by 2 methods, which is like very, very important for any competitive exam. If you're done, if you all can drop a yes in the chat box, I'll clear the screen and go to the extraction of aluminium. Whoever copied, you can drop a message as yes. We'll go for it. Excuse me. Yeah. So let me know. Yeah, we can go forward if I get a yes from all 4 of you in the chat box. I need 4 yeses. Otherwise, let's end the class because no use of me just writing and talking, right? So if I get a yes from all 4 of you in the chat box, I got a yes from Adyasha.
Yes, ma'am.
Anjali also. Dairya and Mohammed. Jafar. I want to complete the extraction of aluminium and extraction of sodium today. Then we have this Ellington diagram of a metal, which is important. Dairya, are you there?
Yes, ma'am.
I've been 100 times asking to drop a yes. Extraction of aluminium. So, extraction of aluminium, first of all, it's purification of bauxite. Bauxite is the ore. First, let's purify it. There are again 3 methods. Okay, the first one is Bayer's method. Second, Howell's method. Serpek's method. This whole extraction of aluminium is very important. This is the whole metallurgy. The questions frequently asked would only be from aluminium. So, see, this is used for red bauxite containing Fe2O3 and silicates as impurities. This is used for white bauxite and silica. Silica is different from silicates, please be clear. This is again same for red bauxite, with Fe2O3 and silicates as impurities. Okay, so it is Al2O3.2H2O plus you're reacting this with sodium hydroxide at 190 degrees Celsius and 8 atmospheres. We have 2NaAlO2, which is a soluble product with water. And whatever Fe2O3 is insoluble, so it is separated. So separated as red mud by filtration. Okay. Solution is diluted with water and seeded with means just added with freshly prepared. ALOH thrice. And this ALOH thrice is filtered, leaving the silicates in the solution. So we hereby cleared both the Fe2O3 and silicates also. So I want to write the equation related to it. I'm just clearing this first part and writing. So reactions only. Sodium aluminate reacts with water. We have sodium hydroxide coming back along with aluminium hydroxide precipitate. So this aluminium hydroxide at 1473 Kelvin is becoming Al2O3 plus water. So this reaction Al2O3.2H2O reacts with sodium carbonate used. Again, you have 2NaAlO2 plus CO2 plus H2O. NaAlO2 reacts with water and carbon dioxide. At 60 degrees Celsius, it gives rise to aluminum hydroxide plus Na2CO3. Again, the 2ALOH thrice at 1473 Kelvin gives rise to Al2O3 plus 3H2. Different process. This again, Al2O3.2H2O reacts with 3C and N2 180 degrees Celsius in an electrical furnace. Gives rise to 2 aluminium nitride plus carbon dioxide plus water. And if it is 2 aluminium nitride, we are trying to dissolve this in water. And again, we have aluminium hydroxide as the precipitate along with ammonia gas. So the silica, whichever is there, is reacting with carbon monoxide to produce carbon dioxide and silica. Because silicon, it volatilizes at this temperature. So the 2 aluminium hydroxide at same 1473 Kelvin gives rise to Al2O3 plus water. Next, we have the reduction. Now it is only purification. Are you done? In the solution. Next, we have electrolytic reduction. Paul Herold's process. So whatever we purify, na, aluminium, Al2O3 was one of the final products in all the reactions. So the second step is the purified Al2O3 is actually mixed with cryolite. Cryolite also mixed with calcium. This is called fluorspar. Why are we using these two? Because it helps in lowering the melting point of the mixture. It also brings the conductivity. So the whole fused mixture is electrolyzed. Steel cathode and graphite anode are used. So graphite is used in reduction of metal. The overall reaction would be so the electrolysis is carried out in electrolytic cell with carbon electrodes. So oxygen liberated at the anode, okay, it reacts with the carbon electrodes. It reacts with the electrodes wala carbon. And produces CO2. So actually, per 1 kg of aluminium, 0.5 kg of carbon anode is burnt off. So you have to replace it again and again. So what happens at cathode? Al3 plus, it melts. 3 electrons it loses and becomes Al in the liquid form. At anode, we have two reactions. Carbon reacts with the oxygen, forms carbon dioxide mostly, sometimes carbon monoxide, depending upon the oxygen present. And we have the aluminium. Final aluminium, this is called Hall-Herold's process, which is the electrolytic reduction method of aluminium. One more, just small part is the extraction of sodium. If we are done with that, I'll continue Thursday. So let me know once you're done. I'm clearing it. Extraction of sodium. Extraction of sodium. Okay. Fused mixture of NaCl and CaCl2 is taken in down cell. It is a type of electrolytic cell. So which consists of, what will it consist of? It consists of a circular iron cathode and a carbon anode On passing electricity, what happens? First is ionization of NaCl that takes place. Next is collection of sodium at cathode. Reduction. Collection of Cl minus at anode. Cl minus plus electron gives rise to Cl, which is oxidation. So that Cl plus Cl combines to form Cl2. Other method is Na can be obtained by also electrolyzing molten NaOH in Kastner cell. See, how much is given, that much is enough. They'll just ask you in Kastner cell what happens. It is NaCl reacting with like NaOH is being electrolyzed, or WeXL NaOH is being electrolyzed. If they ask you, it's in Kastner cell. So this much is about the extractions of these 4 types of metals. So if you have copied this, you can leave the class. We're done for the day. We'll continue with the aluminum diagram in the coming class, which is very important.
Okay, ma'am.
Which is the thermodynamic part, and sort of there's so much to talk about it. And we also have some extractions of iron and other metals also. Copper, important methods of extraction of iron, extraction of copper, extraction of zinc, and also some more methods of extraction of magnesium, and so on. I think it's a huge chapter, metallurgy. We'll need this week and also maybe some of next week also. I'll see you again. Thank you.